us from Kenya to talk about some of his research, and he's joining us over Zoom. So this is not directly related to ASSA, but will be more research. Right. Vincent, are you there? Can you hear me?
Yes, can you hear me?
We can hear you. Would you like to share your screen?
Yes, I can share my screen.
Great, thank you very much.
Okay, thank you.
Looks nice in Kenya. There we go.
Can you see my screen?
We can see it, thank you.
Okay, thank you. Greetings to professional astronomers, amateur astronomers, and upcoming astronomers. I deliberately introduced a third group, or create a third group, upcoming astronomers, because that is the group that I represent. You know, sometimes you may feel nervous, or even it's challenging to actually do a presentation after your seniors. But it also comes with advantage. For example, by the time you will be making a representation, you would have learned a lot, including what to do and what not to do, plus many more. I'll not say much because of time. I'll just go direct to my research topic. Just like I have been introduced, I'm from Kenya, and a final year undergrad student taking applied physics and specializing in astrophysics. I did my undergrad project on one of the most interesting fields, that is gravitational waves, using another very new and interesting field of machine learning. So even having to speak in this conference, especially including my seniors here, I think it's not a total waste of time, because I'm coming with at least a fresh idea, because we are talking about gravitational waves which were just first detected in 2015, and machine learning, which is just a new field of study, and both of them they're providing fresh ideas into the field of study, and that's astronomy. Direct to my research topic, classification of gravitational waves with machine learning, and in this, it's about testing different machine learning algorithms for identifying gravitational waves. Now, because of time, my representation will try to, most of the time, to speak for itself, because I may not be able to mention everything. So even from the slides, I think you can see it's like they are communicating. So if I may forget to mention something, the slide may help you to understand some of them. I'll start by giving basics of what are gravitational waves, and then I will talk about my data and maybe something about machine learning if I can represent my results. Gravitational waves are simply disturbances or ripples in curvature of space-time, and they carry gravitational wave energy. They come from, the sources are from there are two sources, that is cosmological sources and compact binary covalence. That is the result of depth of stars. That is the result of stars when they die. They either result into black holes, neutron stars, or white dwarfs, depending on the size and the mass. So cosmic events include events that happened during the early universe, and events like the Big Bang or smashing of black holes. Compact binary covalence includes binary systems like binary black holes, binary neutron stars, binary white dwarfs. Now, how are they detected? Though this one I will talk about it in the next slide, but the simple method of detection is simply what we call laser interferometry. This one will be discussed later. Why study gamma waves? Gamma waves, one thing is very unique in terms of they provide unique information. Another thing is that they supplement other sources, and then they also complement other sources. The previous speakers, especially during the morning hours, they talked about multi-wavelength astronomy and multi-message astronomy. This gamma wave astronomy is very unique and is one of the fields, fresh field of what we call the future of astronomy, that is multi-message astronomy. So it's of great interest because from them we'll be able to understand events that happened in the early universe, we'll be able to actually approve some of the fundamental or study some of the fundamental laws of physics, like general law of relativity. That is Einstein's law. We'll be able to know more about black holes, those compact binary systems, rate of expansion of universe, most of the things we do know through the study of gamma waves. You can see on what is this one is simply those people who are familiar with the relativity. These are the Einstein field equations. On the left-hand side, is simply summarized as it tells the left-hand side tells the body how to move. Like you can see the body moving around the fabric of space-time. That's what we call the space-time, like the fabric. Just think of space-time as fabric that bends when mass is placed on it. So the left-hand side equations where you have the mass of the body and all those ones simply tells the body on how to move, but the left-hand side tells the space-time on how to curve. So that is the relationship. This is what I was talking about in terms of principle of detection. This just helped me understand my methodology. For example, what happens is that the interferometers, the observatories are such that they are somehow out of what we call antiphase, like they are 180 degrees out of phase, and that means they will cancel each other. So if there is any slight change, and slight change happens in what we call quadrupole moments. Quadrupole moment is where they are L-shaped, so that when one end shrinks, the other one extends, and then the waves can be detected. Though these are exaggerated simulations, you can see the effect of the waves on our Earth, but these are exaggerated just to make us understand. This is what happens. You can see just what I've explained. The arms, the two arms of the interferometers, the mirrors, the test masses, you can see them, and then you can see how the space-time, how the movement of black holes affects the bending or the curvature of space-time. And this is detected, you can see from the template on the right-hand side. You can see the bodies, how they move. You should take key in terms of the frequency, in terms of the velocity. Maybe this one was clear in the previous slide, that you show that as they approach each other, the velocity increases, the frequency also increases, but the distance between them reduces. So they become until a point of what we call the point of merger, when they are now, they smash together and then form one object. And this is what we call the ring down now frequency. That's what happens. Now, what is just below that is what is actually observed from the screen. You can see the strain and the effects of strain with the time. The highest frequencies where we have the what we call the measure and then ring down, when the frequency now flattens. Why do this study? Is because of huge amount of data that is being received for reasons like the number of observation runs have been increasing, the time that observation runs are being conducted are increasing. This comes with huge amount of data. The instruments, in terms of the number of instruments, like initially we had LIGO, then now we have LIGO Hanford, we have LIGO Lavington, we have the Vigo in Italy, we have others coming up like the LISA that is maybe be operational by 2030. We have others like geo. We have a lot of instruments, and their sensitivity being improved. Like for example, we are now in third generation of the instrument. So it means more and more events are likely to be detected. Then methods that are currently available are like, for example, human inspection, which is biased, tiresome. You know how we come with other challenges. And methods that are available are still like hard-coded algorithms, much filtering, which have a lot of challenges because like they involve human in terms of the outcome. It heavily depends on the capacity of the human. Objectives main is simply develop and test different machine learning algorithms. And then you build your model, you test different using different machine learning algorithms. I will try to explain what is machine learning after explaining maybe gravitational waves. Now I'll talk about my data that I used. The data I used came from European Gravitational Wave Observatory, and they are provided at Kaggle. This is an open source, everybody can access them. They were simulated data, simulating signals from various three observatories. And for we to confirm that it's actually an actual event, the event must happen, must be confirmed from at least two of the three observatories. Because otherwise, if it's detected in one and the other one, then it may be noise. One of the challenges with the detection is noise because it involves detecting changes to less than subatomic particles. That means that less than the size of subatomic particle, that is 10 power negative 21. So you see, it is prone to noise because any of these changes can happen. So it's noise. So that is one of the challenges. That's why we have to be very precious here. Then how was this data generated? It's simply, you have to consider factors like the masses of the objects if they are black holes. We have to consider the mass of each object, because the heavier the mass, the heavier the effect on the curvature of spacetime, and then the most likely the event is to be detected because it will generate a lot of energy during maybe the major process. Then the spin and the distance. The distance is distance between the two objects. Like when they are moving, like we could see how they are approaching, and those are some of the factors you need to consider when generating your data, especially simulated data. Data preparation, this involves this now some part of machine learning because you have to visualize the data to understand it better, and then tokenization, or once you have understood your data, and then you need to convert it into a text kind of data that machine learning, because it can only interpret specific kind of data, not the way we collect it like in time series. You know, the data is collected in time series with those wave-like plots. Data augmentation, this simply involves kind of modifying your data. This can involve copying, because sometimes you may need to modify your data to make your machine learning model to understand it. This can involve copying sometimes if you have found some of your data with prominent features. For example, the frequency are higher, like in terms of, I mean the displacement from the zero amplitude, then it's easier to use it to make the model to learn faster. If at all the model is not learning fast, you can go ahead and synthesize your data. This involves now you have to define it in terms of, because advantage of synthesized data is that you are able to know the kind of noise, whether Gaussian or not, because initially it's not easy to tell from data that you didn't generate yourself. You don't know the kind of noise, whether Gaussian or not, and how. So it's good to also generate your data so that you make the model learn, and then you apply whatever model you have generated to test with your data now. One of the things, once you have done all those things, you need to set up parameters and many other factors. These are factors like, for example, you have to consider factors like CPU time, the size of the data that you need to make the model learn full, because sometimes you can give it a lot of data and then it has learned what is enough to now perform, but you have to consider whether you are like overworking the model, especially this comes when you have computational challenges. So you have to set parameters like number of epochs, size of the data, the patch size, yeah. So algorithms that are used are convolutional neural network for 1D. Once you have understood your data, you should be in a position now to kind of maybe suggest the algorithm that can be applied for your data. For example, this is time series data. Best algorithm for time series data are convolutional neural network, simple neural network, recurrent neural network, and maybe LSM, which is called long-term short-term memory. They're the best for time series data. So this is why I came up with I'm just trying to explain how I came up with the algorithms. Why? Because there are over 100 algorithms, but I came up with these 5 just to test in terms of which one works best. Once you have suggested this, you now have to build your different models with different algorithms. Then you train them and see whether they're learning and make some changes in parameters and data preparation, because data preparation heavily depend on the kind of algorithm that we're using. Yeah. Then you test in terms of the accuracy. The next is I simply give, because this is a wide topic and very interesting, I will not go into details, but I will simply take 2 algorithms maybe to explain because they perform better than others.